What's going on, linear algebra bros? In this video, we're going to be working with linear combinations, specifically a linear combination involving vectors from a polynomial space, perhaps P sub 2. Now, the problem wants us to express the vector P. This is a second degree polynomial written in reverse standard form, which is typically how the author of our text likes to write the polynomials. We want to write this vector P as a linear combination of the vectors P1, P2, and P3. Now, if we want to approach this solution from scratch, we can, and I think it's helpful to do so. But you'll see that, if you watch the other video, you can pretty much apply the same technique as we were doing with augmented matrices, using the coefficients instead of components of these polynomial vectors. Now with that, the idea here is to see if we could rewrite this polynomial vector P as a linear combination of P1, P2, and P3. So it boils down to finding scalars, the first being K1, which gets multiplied to P1, added to K2, P2, plus K3, P3. The problem boils down to seeing if we can identify values of K1, K2, and K3 that allow us to write the vector P as this mixture. Now, the polynomials are what I'm going to bring in next. The polynomial P is 7 plus 8x plus 9x squared. And over to the right, each one of these scalars you want to set in front of a set of parentheses, because each polynomial has multiple terms. And P1 has the terms 2 plus x plus 4x squared plus K2 times 1 minus x plus 3x squared plus K3 times 3 plus 2x plus 5x squared. Now what we're going to do is distribute the scalars to clear parentheses, and upon doing so, I'm going to shuffle around some terms, and you'll see why I do that in just a moment. 7 plus 8x plus 9x squared on the left, and on the right, I'm going to start with 2k1 plus k2 plus 3k3. Now, if you're wondering where these terms are coming from, it's basically the sum of the constant terms once these scalars are distributed. So for example, with k1, when you distribute it, one of the terms you get is 2k1. First term you get upon distributing k2 is k2. And then the first term you get upon distributing K3 is 3K3. And that's exactly what I have right here. Moving on, I'm going to write plus K1x minus K2x plus 2K3x. And very similar thing. All right, these are the terms you get when you distribute each of the scalars to the linear terms involved in the polynomials. So K1 times x, K2 times negative x, K3 times 2x. Last but not least, plus 4k1 x squared plus 3k2 x squared plus 5k3 x squared. And it might go without saying, but I'll say it anyway. These are the three terms you get when you distribute the scalars to the squared terms involved in each one of these polynomials. Now, I'm going to do some factoring on the right-hand side. I'm actually going to leave the first three terms as they are, but I will put it inside parentheses, the expression that is. With the next three terms, I'm going to factor out a copy of x, in which case this would be left over with the terms k1 minus k2 plus 2k3, and I'll place x directly to the right. And then I'll factor out x squared with the last three terms, which upon doing so would leave behind 4k1 plus 3k2 plus 5k3, and then x squared directly to the right. Now the reason why I did it this way is because of a little fact from pre-calc, and we can actually piggyback on a fact about vectors from this course. The only way that two vectors are equal to each other is if and only if their corresponding components are equal. And you can kind of riff on that with polynomials. The only way two polynomials will equal each other is if they have the same degree and the coefficients are equal to each other. I'm probably not saying that in like the most proper way, but I think you know what I'm trying to imply with all that. Here's what that is. So in order for the polynomial on the left to equal the one on the right, then it has to be true that 7 equals this expression, 8 equals this expression, and then 9 equals this expression. So we end up getting a linear system, and I'm going to flesh that linear system out. 2k1 plus k2 plus 3k3 equals 7. k1 minus k2 plus 2k3 equals 8. And then 4k1 plus 3k2 plus 5k3 equals 9. And what you can do is bounce this into augmented matrix format. And one thing I want to point out is that the columns that are to the left of the augment bar happen to be the coefficients of our polynomials p1, p2, and p3. Case in point, 2, 1, and 4, those are the coefficients of our polynomial p1. 1, negative 1, and 3 are the coefficients of our polynomial p2, and 3, 2, and 5 are the coefficients of our polynomial p3, and then 7, 8, 9, feeling fine, are the coefficients of our polynomial p. So if you're hip to that, you can just jump straight from the very start of the problem to augmented matrix format. No reason to keep reinventing the wheel with my derivation here, but the teacher in me still wanted to show it to you. And I'll provide the RREF version of this matrix, in which case we do get values of k1, k2, and k3. Specifically, k1 equals 0, k2 equals negative 2, and k3 equals 3. Now let's see what they're asking us for. It says express the vector p as a linear combination of the vectors p1, p2, and p3. So we are able to do that now that we have the scalars or coefficients k1 through k3. So let's form our answer. P equals, we don't need any copies of p1, but I'll write 0 p1. We do need minus 2 copies of p2, say minus 2 P2, and we need 3 copies of P3, so plus 3 P3. And that would be how we express the polynomial P as a linear combination of 0, -2, and 3. I know this video is kind of going long, but this is kind of a cool thing to see if you check it. Our polynomial P, 7 plus 8x plus 9x squared. Now according to our scalars, K1 through K3, 0 times P1, which I'm just going to write that as P1 because I think you all know what's going to happen with the scalar of 0, minus 2 times our polynomial P2 plus 3 times our polynomial P3 we want to know if we simplify the entire right-hand side and clean things up and write it in reverse standard form, whether or not we'll get the polynomial on the left. So let's see about that. Okay, we know that this is going to go to 0. Let's distribute the -2. Let's also distribute the 3. And we will clean everything up. -2 plus 9 gives us 7. 2x plus 6x gives us 8x. And then -6x squared plus 15x squared gives us 9x squared. And bada boom, bada bing. What a wonderful thing. That definitely equals 7 plus 8x plus 9x squared. And that is verified. The fact checkers would be proud. All right. So thanks for gritting and bearing through this long video. As always, let me know if you have any questions. Otherwise, I'll see you in the next one.